Hi, we are Group I7 from VIT Pune, and our topic is direct memory access. Today, computers are all around us. From the smallest remote to the largest data center, we are surrounded by computers. One of the aspects that made computers so popular was the sheer extensibility. You could connect multiple devices like keyboards, mice, USB drives, and more at the same time. This may seem insignificant to us, but a great deal of work is put in to maintain the speed and coordination between these devices. Consider you have a computer which you want to play games on. It has a graphics card that has to process every frame your computer displays. To maintain a smooth image, the computer must display at least 60 images in a second, that is 60 frames per second. The graphics card thus has to generate one image every 16 milliseconds. Now, a conventional CPU today operates at about 2 GHz. To simplify this, we can think of it as the CPU can perform 2 billion calculations in a second. Now, one frame every 16 milliseconds may not seem much to a 2 GHz CPU, but when we take into account the fact that the GPU can do 2600 billion operations per second, we start to see the problem. If the result of every operation goes through the CPU before being stored, the CPU will be perpetually busy and won't be able to keep the other functions running, like the operating system itself. That's where direct memory access, or DMA, comes in.
DMA stands for Direct Memory Access. It is a process to transfer data between the memory and the input-output system of a device without direct involvement of a CPU unit. This process is used to transfer large amounts of data more efficiently than the conventional methods. It consists of four components: the DMA controller, device, memory, and CPU. DMA controller. It is responsible for managing the data transfer. It controls the data transfer between the device and the memory. It has direct access to the system bus. The DMA controller typically has its own memory buffer, which can be used to temporarily store the data during the transfer. Device. The device needs to transfer data, initiates a DMA request to the DMA controller. This could be a hard disk, network card, or other input-output device. Memory. The memory is the location where the data is transferred to or from. This could be the system memory or any other dedicated memory on the device. CPU. The CPU is not directly involved in the transfer process. Instead, it sets up a DMA controller with certain transfer parameters and waits for an interrupt signal when the transfer is complete.
During the DMA transfer, CPU can perform only those operations in which it doesn't require the access of system bus, which means mostly CPU will be in block state. For how much time the CPU will be in this state will depend upon the modes of the transfer. Now there are three types. The first one is the burst mode. In this mode, a burst of data is transferred because CPU take control of the buses back from DMAC. This is a quicker mode of DMA transfer, as a huge amount of data is transferred in a very small time and a lot of time is saved. Cycle stealing mode. In this, slow I/O device will take some time to prepare data, and within that time, CPU keeps the control of the buses. Once the data or the word is ready, CPU gives back control of system buses to DMAC for one cycle, in which the prepared word is transferred to memory. The advantage is that it is most efficient for DMA transfer, but the disadvantage is that the rate of DMA transfer is very less. The third type is interleaving mode. When CPU does not require the system buses, then only control of the DMA will be given to DMAC in this mode. CPU will not be blocked due to DMA at all. This is the slowest mode of DMA transfer, since DMAC has to wait for so long time to just get the access of system buses from the CPU itself.
Let us understand the working of a DMA controller, that is, a DMAC, using a simple example. Consider that we have to print a very high resolution poster. We have the poster data stored in a USB drive that is connected to our computer and want to transfer it to a printer which is also connected to the computer. If we transfer it through the processor, it would take a really long amount of time, but we are in a hurry. Moreover, we have to send some urgent emails too. So what can we do? Of course, we use DMAC to offload the transfer. The USB drive, that is our storage device, first requests a DMAC for a transfer to the particular I/O device, that is our printer. The DMAC will now request the initialization of the transfer from the processor. The processor then finishes execution of the current instruction and then sends the hold acknowledgement to the DMAC. This means that the processor has released the control of the address and data buses to the DMAC. The processor then goes on to execute the further instructions while the DMAC, which is the new bus master, now sends an acknowledgement signal to the USB drive and asks it to be ready for DMAC service. The DMAC then generates address and control signals to execute the transfer. Note that during this process, data does not pass through the DMAC. It goes directly from the USB drive to the printer. Once the transfer is complete, the DMAC then sends an interrupt to the processor. The processor takes back control of the address and data buses and continues further execution of instructions, while the DMAC waits for the next DMA service request. This transfer can take place the other way too. For example, a graphics card can directly store a large amount of data without processor intervention. Overall, DMA transfers can significantly improve system performance by reducing CPU overhead and allowing for faster transfer rates.
I am going to explain the advantages of DMA. Faster data transfer. The DMA transfers the data directly between the device and memory without CPU intervention, so the read-write task gets speed up. It decreases the clock cycle needed to write or read a block of data, and it also reduces the workload of the processor. The DMA allows for more efficient use of system resources, reducing the time required to data transfer and freeing up the system resources for the other tasks. Improved system responsiveness. The DMA can improve the system responsiveness by reducing the time required for the data transfer and allow the CPU to perform other tasks.
Direct memory access refers to the process of retrieving or storing data in the memory of the computer system. While this process is essential for most computer programs, it also comes with certain disadvantages. Let's see some main disadvantages along with their examples. First, slow performance. Direct memory access can be slow compared to other operations in a computer system. This is because accessing data in memory requires the processor to wait for the data to be retrieved from memory, which can take several clock cycles. For example, if a program needs to access data from a slow disk drive, it may take several seconds for the data to be loaded into the memory. The second disadvantage is that limited capacity. Memory capacity is limited, which means that program can only access a certain amount of data at a given time. This can be a problem for programs that need to process large amount of data, such as video editing softwares or scientific simulations. For example, a program that needs to process a large data set may need to use multiple memory blocks or paging techniques, which can slow down the program's performance. Third disadvantage, that complexity. Direct memory access can be complex, especially in systems with multiple processors or in disturbed systems. This is because data may need to be synchronized between multiple processors or nodes, which can cause delays and errors. For example, in disturbed database system, multiple nodes may need to access the same data simultaneously, which can cause conflicts and inconsistencies. The fourth disadvantage is that is security risk. Direct memory access can also pose security risk, especially if the data is sensitive or confidential. This is because data in memory can be accessed by other programs or users, which can lead to data theft or corruptions. For example, if a program stores a user's passwords in memory, a malicious program could potentially access and steal the password.
Today I'm going to talk about the applications of DMA. So some of the common applications include, firstly, hard disk drives. DMA is used in hard disk drives to transfer data between the disk and memory. This allows for faster data transfer and reduces the CPU overhead, improving overall system performance. Second, networking. DMA is used in networking devices such as network interface cards to transfer data between the network and memory. This allows for faster transfer of data and reduces the CPU overhead, improving overall networking performance. The third point would be audio and video processing. DMA is used in audio and video processing applications to transfer large blocks of data, such as video frames or audio samples, between the device and memory. This allows for faster processing and reduces the CPU overhead, improving overall system performance and efficiency. Fourth, graphics processing. DMA is used in graphics processing applications to transfer large blocks of image data between the graphic card and memory. This allows for faster rendering and improves overall system performance.